Ladies and gents, my name is Brandon Stover. Welcome to the How to Solve Climate Change course from Plato University. Causes, systems, obstacles, solutions to this global challenge is what you're going to learn here today. When you're ready to learn more skills, join us for free at plato.university. Let's get started with today's lesson. We'll have our expert guests briefly introduce themselves and their credentials for why they are able to speak to this topic.
I am Judith Curry. I received a PhD in geophysical sciences in 1982 from the University of Chicago. I am Professor Emerita at the Georgia Institute of Technology, where I served as Chair of Earth and Atmospheric Sciences for 13 years. Previously, I held faculty positions at Purdue University, Penn State University, and the University of Colorado at Boulder. My expertise is climate dynamics, extreme weather, prediction and predictability of weather and climate, philosophy of science, and decision-making under deep uncertainty. I have been elected as a Fellow of the American Meteorological Society, the American Association for the Advancement of Science, and the American Geophysical Union. My research has been recognized by the Henry J. Houghton Research Award from the American Meteorological Society. I am also president and co-founder of Climate Forecast Applications Network, or CFAN. I founded CFAN to translate cutting-edge weather and climate research into forecast products and services that support the management of weather and climate risk for public and private sector decision makers. I have been frequently called upon to give U.S. congressional testimony and serve as an expert witness on matters related to weather and climate.
Explain succinctly what climate is from first principles.
A changing climate has been the norm throughout the Earth's 4.6 billion year history. The Earth's temperature and weather patterns change naturally over timescales ranging from decades to millions of years. Natural variations in climate originate in two ways. Internal climate fluctuations exchange energy, water, and carbon between the atmosphere, oceans, land, and ice, which changes the surface climate. External influences on the climate system include variations in the energy received from the sun and the effects of volcanic eruptions. More recently, human activities are influencing climate by changing atmospheric concentration of carbon dioxide and other greenhouse gases, altering the concentrations of aerosol particles in the atmosphere, and through land use and changing land cover. Over the past several decades, the definition of climate change has shifted away from the broader geological interpretation. Article 1 of the United Nations Framework Convention on Climate Change defines climate change as a change of climate which is attributed directly or indirectly to human activity that alters the composition of the global atmosphere and which is in addition to natural climate variability observed over comparable time periods. The UN thus makes a distinction between climate change, attributable to human activities that alter the atmospheric composition, versus climate variability, which is attributable to natural causes. This redefinition of climate change to refer to only human-caused climate change has effectively eliminated natural climate change from the public discussion on climate change. Any change that is observed over the past century is implicitly assumed to be caused by human emissions to the atmosphere. This assumption leads to connecting every unusual weather or climate event to human-caused climate change from fossil fuel emissions. The term climate change doesn't just connote the science of global warming, but also an entire worldview of society. Geographer Mike Hume identifies climate reductionism as a form of analysis and prediction in which the interdependencies that shape human life within the physical world are all correlated with climate change. Human-caused climate change is then elevated to the role of the dominant predictor of societal change. Climate change has thus become a grand narrative in which human-caused climate change has become a dominant cause of societal problems. This perspective was highlighted on the cover of a recent Time magazine with the title "Climate is Everything." Everything that goes wrong reinforces a conviction that there is only one thing we can do to prevent societal problems: Stop burning fossil fuels. This grand narrative misleads us to think that if we solve the problem of burning fossil fuels, then these other problems would also be solved. This belief leads us away from a deeper investigation of the true causes of these problems. The end result is narrowing of the viewpoints and policy options that we are willing to consider in dealing with complex issues such as public health, water resources, weather disasters, and national security.
Why does climate exist? What role does this system play in our lives?
Scientific investigations of the dynamics of the climate system have more in common with systems biology and economics than with laboratory physics and chemistry, owing to the inherent complexity of the system and the inability to conduct controlled experiments. Complexity is not the same thing as complicated. Complicated systems have many parts, but simple chains of causation. Complexity of the climate system arises from the chaotic behavior and nonlinearity of the equations for motions in the atmosphere and ocean, and also the linking of subsystems for the atmosphere, oceans, land surface, and glacier ice.
How might we positively influence this system to help solve climate change?
Striking a balance between the security of basic food, water, energy, and material supplies with the least possible impact on the environment, including CO2 emissions, is arguably the greatest challenge of the 21st century. The UN Paris Agreement has presupposed a moral obligation to control climate change by eliminating fossil fuels and achieving net zero emissions. They have bypassed the moral dilemma of preventing future harm from climate change versus fulfilling our duties to currently living humans. Given our inability to predict what the world of 2100 will be like, and the world population's preferences and values, and this is not to mention our inability to predict the climate in 2100, what kind of legacy can we hope to leave our descendants circa 2100? Beyond a culture of freedom and prosperity and an environment that can sustain, does it make sense to tort current policies around imagining what kind of climate the world's citizens would prefer in 2100? Given our inability to understand the world circa 2100, including likely losses from human-caused climate change, sacrificing the well-being of the current population by restricting energy access seems neither moral nor just. The UN strategy to control the climate or even emissions needs to be challenged. Even if we successfully eliminate CO2 emissions by 2050, we are unlikely to perceive any benefits to the climate in the 21st century. Even beyond the technical issues, greater realism is needed about the uncertainties in politics underpinning the pursuit of control. The pandemic illustrates that our tools for acting on a complex global problem, including experts, precise scientific metrics, computer models, enforced restrictions, have resulted in much less than the desired quality of control. The global energy transition and worldwide transformations to sustainability are far more challenging than the global COVID-19 pandemic. Our hubristic aspirations for control fail to acknowledge the wickedness and systemic aspects of the climate change problem and its proposed solutions. Yes, we can seek to lower emissions as low as reasonably practical, ideally while minimizing our regrets and maximizing our opportunities through the energy transition. But we should not pretend that we are controlling the climate. There is growing support for climate politics that harnesses enlightened self-interest rather than focusing on austerity. This plays to the values of the central objectives of human flourishing and thriving. There are three major policy issues that fall under the climate umbrella: the desire for clean, abundant, and cheap energy, concerns about vulnerability to extreme weather and climate events, and concerns about rising atmospheric concentrations of CO2 and its impact on the climate. Energy system R&D and reducing vulnerability to extreme weather are primarily dealt with by national and subnational entities and can be expected to receive widespread political and economic support since they support local self-interest. On the other hand, reducing global CO2 emissions is politically controversial since international policies have attempted a top-down approach that impacts energy systems and vulnerability to extreme events by the emphasis on rapid reduction of fossil fuel emissions. This has the specter of energy scarcity and a redirection of funds away from development and adaptation. Focusing on energy system R&D and reducing vulnerability to extreme weather is a quieter kind of climate politics, which doesn't require the apocalyptic rhetoric and plays well into local strategies that people can be enthusiastic about. Willing actions are more effective politically and have higher moral legitimacy because of the abundance of coercion. A focus on energy system R&D and reducing vulnerability to extreme weather, while concurrently supporting flourishing and thriving of the global population, can act to de-escalate the political controversies associated with the climate change issue and CO2 emissions reductions. Another strategy is to eliminate the mismatch in timing of the costs versus benefits of energy and climate policies. Any near-term emissions reducing policies should also provide short-term benefits, with the long-term goals of reducing CO2 emissions taking on secondary importance. Clean energy that increases abundance and reduces costs is an example. The reduction of methane emissions from fossil fuel production is another example that has short-term benefits. Adaptation strategies to reduce vulnerability to extreme weather events also provide near-term benefits. Once we acknowledge that we don't currently know how to stabilize concentrations of CO2 on the timescale of decades, and in any event can't control the climate, we can search for new and more effective approaches for improving our energy systems and reducing our vulnerability to extreme weather, all the while focusing on supporting human flourishing and thriving in the 21st century. And finally, we need to recognize that what has been cast as a global climate crisis is, for the most part, thousands of local vulnerability emergencies that are revealed by extreme weather events.
What are the best resources to learn more about climate in relation to climate change?
Here are several book recommendations. For some basic physics of the climate system, there is a book by MIT Professor Carey Emanuel titled What We Know About Climate Change. A book that is more focused on uncertainties in our understanding of the climate system was recently published by Stephen Koonin. This book is entitled Unsettled: What Climate Science Tells Us, What It Doesn't, and Why It Matters. My own book, Climate Uncertainty and Risk, is in press. A book that puts the risks and dangers from climate change into perspective is False Alarm by Bjorn Lomborg. For a realistic view of our attempts to solve climate change, see How the World Really Works by Vaclav Smil.
Right now, you're speaking to passionate students who want to actually solve problems like these. What top 3 skills should they study so that they actually have the ability to do so?
3 different solution-oriented directions are evolving with regards to climate change: big data approaches, climate tech, and wicked science. Big data approaches are an outgrowth of the information technologies that have driven big tech. We now have the capability of collecting and analyzing massive amounts of data. Climate-relevant data are being collected from diverse sources that include smart sensor networks, cell phones, and constellations of small satellites, with an emphasis on geospatial and hyperlocal data. Big data approaches, when interpreted by machine learning and artificial intelligence approaches, have great potential for providing information and knowledge for managing the risks of climate change. Big data analytics are most useful when they are interpreted by human intelligence and combined with theory-driven and/or small data approaches. Another trend that comes from the culture of big tech is climate tech. Climate tech is defined as technologies that focus on reducing or sequestering greenhouse gas emissions or addressing the impacts of global warming. Climate tech entrepreneurs are developing diverse products ranging from carbon accounting software to agricultural technology to electric vehicle batteries to nuclear fusion projects. There is a substantial migration of engineers underway away from big tech and towards the new opportunities in climate tech. Climate tech is currently regarded by many to be a generational investment opportunity and the most exciting space in tech. And finally, we have the evolution of wicked science. Wicked science is a process that is tailored to the dual scientific and political natures of wicked societal problems. As such, wicked science is massively transdisciplinary, including natural sciences and engineering, along with social sciences and humanities. Wicked science uses approaches from complexity science and systems thinking in a context that engages with the political roles and perspectives of decision makers, planners, and other stakeholders. Wicked problems and the strategies devised to address them cannot be defined by scientific experts alone, but include the experiential and operational knowledge of a range of stakeholders. Combining and integrating knowledge from diverse disciplines and other sources to provide insights, explanations, and solutions to wicked problems is a substantial challenge. For the solution orientation of wicked science to be meaningful, we need an overarching philosophy for navigating wicked problems. We need to acknowledge that control is limited, the future is unknown, and it's difficult to determine whether the impact you make will be positive. We need to accept that climate change will continue to disrupt natural systems and human well-being. This acknowledgement helps avoid the urgency trap. By acknowledging that there is no road back, we can focus on the road ahead. The road ahead can be facilitated by broader transdisciplinary thinking about the climate change problem and its solutions. This requires moving away from the consensus enforcing and cancel culture approach of attempting to restrict the dialogue surrounding climate change and the policy options. We need to open up space for dissent, disagreement, and discussion about scientific uncertainty and policy options so that multiple perspectives can be considered and broader support can be built for a range of policy options. Wicked scientists are willing to become embroiled in political debates and thorny social problems. Genuine transdisciplinary understanding and collaborations across disciplines and with a broad range of stakeholders is needed for meaningful contributions to wicked problems.
Any final recommendations for the audience?
A few words about my book, Climate Uncertainty and Risk. Some words from the book description. World leaders have made a forceful statement that climate change is the greatest challenge facing humanity in the 21st century. However, little progress has been made in implementing policies to address climate change in a meaningful way. In Climate Uncertainty and Risk, eminent climate scientist Judith Curry shows how we can break through this stalemate. This book helps us rethink the climate change problem, the risks we are facing, and our response. It helps us strategize on how we can best engage with our environment and support human well-being while responding to climate change. Climate Uncertainty and Risk provides a comprehensive framework for understanding the climate change debate. It shows how both the climate change problem and its solution have been oversimplified. It explains how understanding uncertainty helps us to better assess the risks. It describes how uncertainty and disagreement can be part of the decision-making process. It provides a roadmap for formulating pragmatic solutions that can improve our well-being in the 21st century.
Thank you for taking the How to Solve Climate Change course. If you want to learn the skills to solve this global challenge, join us for free at plato.university for exclusive content, extra resources, and actionable exercises with every lesson. This course was produced by Plato University, where students turn passions into purpose and learn skills to change the world. Learn more at plato.university.